So I hope Raul, you are there again.
Yes, I'm here. Can you hear me?
Yes. So you can share your screen, and we can start again. I think everybody is still connected.
Okay, so hello again. So now what I will explain is the Wi-Fi emulation platform and what the test we have done in order to test if the platform is suitable for what we want to do in this project. So coming back to the picture of the complete architecture of the complete platform, what we are going to see now is this part, which is the one who aims to get IP traffic, convert it into Wi-Fi signals, add interference and a channel model into the RF level, and then coming back to the IP frames. So this Wi-Fi emulation platform, it's made of a Wi-Fi dongle in charge of converting from IP to RF, the counterpart, which is the Wi-Fi access point for the contrary situation from RF to IP. We have the channel emulator in the middle, that in this case it has been the one built for this project. And we also have as an interference generator and a RF jammer that we will see later. And in order to test the platform, what we have is two servers, one in each side. We will see it now. So here you can see a picture of the real implementation of this Wi-Fi emulation platform and a block diagram. So what we can see here is we have here in the right the PC that will be in charge of generating the IP traffic, in which it has connected the Wi-Fi dongle. The Wi-Fi dongle, its RF output, it's connected with an SMA cable to the channel emulator, and the output of the channel emulators, the signal coming out of the channel emulator goes into a power combiner, which combines or adds this output signal with the interfering signal created by the jammer, and the sum of these two signals enters the Wi-Fi access point, which is the one who creates or reconverts the IP frames that in this case are sent into the hyper server. This would be this same chain here in the picture. So here you can see a test summary of all the tests that have been done to the different platforms for both Wi-Fi and LTE tests, just as a reference of what we have tried to emulate. We have some, let's say, reference measurements in order to see that in the absence of a perturbation, everything goes okay. And then we have a test with different channels, with only channels or channels with jamming and so on. And we will see them in this presentation and the following ones. So for testing this Wi-Fi emulation platform, where we have selected these two of the channels that Juan has presented in the previous talk, which are two channels for the cutting, which suits our frequency and bandwidth, and the speed and number of tasks that we are able to emulate. As a reference, what we have used as a Wi-Fi dongle or Wi-Fi access point are these two devices. These are Wi-Fi 11 VGN devices, and we have configured the access point into the channel 11. And as a jammer, we have used a jammer from programmers that it's not possible to control it via software. It's just has some buttons and power selector. And the tests that we have done, they have been done with iPerf in its version 3. And we have run a test of 600 seconds making an average of each 10 seconds. And we have made tests both in TCP and UDP, which are the two ones that allows iPerf. And we have measured the throughput, both for TCP and UDP, the packet error rate for UDP, and also the delay and jitter in UDP. So as I have said before, what we have done first of all is, in the absence of any perturbance and in the absence of even the channel emulator, with the channel configured as a flat channel, just with attenuation, we have made some, which will be the ideal or the best case possible. We have measured all the KPIs that I have just mentioned, and we can see that okay, the best achievable case would be 36 megabits per second in UDP that gets reduced to 31 megabits per second in TCP due to the header overheads, which is quite close to the theoretical 54 megabits per second that can be achieved by this Wi-Fi at RF. As there's no channel, no perturbance, anything, we have no packet loss, and the jitter is quite low. Once we start programming these channels, which has a multipath effect and so on, into the channel emulator, we see that the throughput lowers, both in TCP and UDP. The jitter rises a little bit, and that's because there are retransmissions at RF level. Even if at IP level we cannot see them, at RF level, the Wi-Fi stack takes charge of missed packets. So what it does is make its retransmission. So that's why the jitter rises. But these retransmissions also make that the packet error rate remains into 0. If we only test the jammer, it's a flat channel plus the jammer. What we do is with the jammer is activating it and deactivate it each 2 seconds, 1 second on, 1 second off, in between the instant 10 seconds and 500 seconds of the test, which can be seen here in the throughput. Just as a reference, we see that at the beginning there's nothing, and in this moment the jamming appears. We remain jammed up to here, and then it comes back again. So what we do here is during the time that the jammer is active, there's a great degradation both in the throughput, in the jitter, and in this case even in the packet error rate. In case we don't apply a pulsating interference, but we just enable the jammer, the link goes completely down. I mean, there's so much packet loss that it's not able to recover it. And finally, in a mixed setup in which we have both the channel model acting and the jammer, what we can see is again that during the time the jammer is active, there's a great degradation of the results. Actually, the jammer effects are greater than the channel effects. It's more destroying the jamming effect than the one from the channel, but it's something expected. And again, if the jammer is continually enabled, the link also goes down. So which can be the conclusions of this test? Okay, with respect to the reference measurements, obviously, as the propagation channel deteriorates, either because of the multipath effect, the Doppler, and all the rest of the effects, the throughput decreases and the jitter increases. In this case, as a Wi-Fi in its own protocol has retransmissions at RF level, usually there's not packet loss. So only due to the retransmissions, the throughput and the jitter get worse, but we don't miss packets. For this, it also helps that the Wi-Fi MAC access layer implements the CSMA CA. So the Wi-Fi transmitters doesn't transmit in case it sees power in the channel. So in case of the jammer, when the jammer is acting, we don't lose packets because the transmitter doesn't send them. Obviously, if the jammer is continuously on, we lose the connection because the transmitter cannot transmit. But in the end, the main conclusions can be that, okay, the platform is valid for IP level emulations with real RF channel emulation. And that would be all.
Okay, Raoul, thank you. I propose that Laurent, you or Sofiane, I don't know, you continue with the second Wi-Fi platform.
Yeah, it's me, Marion. So
okay, so you can share your screen.
Yeah, just a moment, please. Okay, share screen. Is it okay, Marion? You can
Yes,
see the
yes,
screen?
it's okay.
Okay, that's good. Hello, everyone. It's Sofiane from University of Lille, and now I will present for you some of our results for Wi-Fi channel emulations within the framework of the Emulradio4Rail project. So the context is summarized as follows. Our main goal is to emulate full Wi-Fi communication in the context of railways. So the Wi-Fi communication will be between an access point and a normal device. One of them is on board and the other one is on ground. Also, we want to include some interfering signals in order to see the effect of like phenomena on the IP level KPIs. For the interference, for the single interfering radio signal, so we will make use of the type 1 scenario. For the outlines, we will present the testbed, the interference scenarios, the automatization step and remote control for the whole testbed, the Wi-Fi emulation with interference results, and we will finish with concluding remarks. So for the testbed, this is a really simplified figure for the testbed. Mainly, we have two computers. They are communicating through to the Wi-Fi protocol, and instead of having the RF waves, so they will be linked through the coaxial feeders. And since we intend to make the emulation on the downlink side, so we have to separate both links. It means the downlink and the uplink through the RF circulators. And between both of them, we will set up all our instrumentations. So point A and point B here, they refers to the instrumentation input signals, and the point B for the output emulation signals. So for the instrumentations, mainly we make use of the Keysight BXB baseband channel generator and channel emulator. So since it's a baseband channel emulator, so at its input we need the down converter, which is the VXA signal analyzer, and on the output of the channel emulator we have to set up up converter, so which is the ESG in this case. So here we have some print screens of the soft of the channel emulator. We can see that we have so many pre-configured channels, even for railway scenarios. And also at the same time, we can customize our channel model. So we can put our own parameters. Here, if, for example, we can make use of MIMO scenarios, or also we can exploit the MIMO scenarios for introducing interference configurations. Here we have a photo for the real test bed. As we see, we can see all the instrumentations, the ESG, the PSG, the channel emulator. And also here we have the point A and point B to refers from the input and output signals between our instrumentations. Here we can see all the hardware except of the access points because they are so far away from the main test bed in order to avoid any RF leakage. For the Wi-Fi emulations, in the first time we did some preliminary channel emulations. So these preliminary emulations are done using two different channel models, while for the second channel, he has a higher time spreading. And after that, we will observe the KPI indicators on the higher IP level. For the results, first we see here the throughput. So we see that the effect of time spreading on the throughput. So we can see that on channel 2 we have less better performance than the channel 1 in terms of throughput. Also the same thing for the LTT or the round trip time. We can see that on channel 2 we have the worst results. Once we introduce the velocity or we consider velocity in the channel emulations, here we can see the evolution of 3 KPIs, the bandwidth, the jitter, and the packet loss. Here we can see the evolution or the impact of the velocity on these KPIs. So here, as obvious, so we have degradation of the 3 KPIs in terms of velocity. So for the interference, we have so many scenarios. We have scenarios for or options for the RF scenario and for baseband scenario. So the option A for adding interfering signals is the most realistic one, or the most or the closest one to the reality, since we add a real Wi-Fi signal to the main communication. So here we see that we have another independent Wi-Fi communication, and at this stage we will add the interfering signal through the RF combiner. The option B is always an RF case, but instead of having real Wi-Fi signals, we generate them, for example, through MATLAB and with the arbitrary waveform generator. The same thing for option C, but for the option C, we can generate the interfering signals inside or from the inside of the PX bay or the channel emulator, as it's in the same time channel emulator and the signal generator. The options D and E are in the baseband case. So here we generate our interfering signals, and after that we make addition in the baseband. When we say in the baseband, it means just before the entry of the channel emulator or the PXB. So for the automatization and remote control, for automatizing tests, we programmed MATLAB scripts. So within these scripts, we can use the kind of KPIs, the number of tests, the frequency or the delay between the test batches. And also these scripts, they allow us to generate automatically the statistics on the results. At the same time, we can control or fully remotely control our test bed through SSH sessions. So for the results, here we have the full configuration or the final configuration that we make use. So as you see, we used the scenario A or the option A for adding interference. As we said before, it's the most realistic one. Here is the photo for the RF connections. Here the point from the access point 1 and from the access point 2. The access point 1, it refers for the main communication, and the access point 2, it refers to the interfering signals. So here to USB dongle 1, which is always related to the main communications. So for the test settings, we have about 2000 iPerf trials, 18 tabs TDL channel models, and for the main communications, we look the channel 1. When I say channel 1, it refers to the main communication to the 2.512 gigahertz Wi-Fi channel. For testing the different scenarios of interference, so here we considered 3 scenarios. So the co-channel interference, the adjacent channel interference, and the open channel interference. So open channel interference, it's almost no interference case. For the results in the TCP case, we plotted the tail function, the estimated tail function. And here we can see the effect of each of the scenarios of the interference on the TCP bandwidth. The same thing for the UDP result, but we considered the CDF. And here we have a plot for the jitter time. So here we can see the effect of the interference on the open channel case 1 to 6 and the adjacent channel interference, which is 1 to 2. To conclude, through this test, we can say that the emulation with interference is really possible, and it gives a realistic representation of the communications. Also, the testbed that we have installed is really for so many scenarios and so many cases considering interference. We also can use it for other kind of perturbations. So it offers a large flexibility and possible implementation of other TDL-based channel models. We have studied so many solutions in order to introduce interference. And IP level KPI can be easy obtained through the scripts that we set up for generating automatically all the required tests. Thank you for your attention.
Okay, thank you very much, Sofiane. So I think we have a view of what we obtain with the Wi-Fi. The experimental assessment, the aim was to obtain statistical variation of the IP metrics, and this will be presented later by Laurent. Now I leave the floor to José to present the open air interface.
Thank you very much, Marion. Can you hear me?
Perfectly, yes.
Perfect. Then let me share my screen. Yes.
Before José starts, you can ask questions in the chat, and we will have, I hope, some slot for question at the end.
Perfect. Can you see my screen now?
Yes.
Okay, so then I'm going to start. So the aim of the presentation is the LTE subsystem in the overall Emulradio emulator, and it is based in open air interface. I'm José Soler, I'm associate professor in the Technical University of Denmark. Then, like my colleagues before, I'm going to introduce first the institution. Let me see. Yes, the TU, the Technical University of Denmark, is one of the main universities in Scandinavia, and it's almost 200 years ago. It was created by the discoverer of electromagnetism, Hans Christian Ørsted, who was by the time teacher in Copenhagen University. And he considered that the teaching there, it was too theoretical, and he liked to get dirty hands in his teaching and showing experiments to the students. So he decided to create his own academical institution, which was the origin of the current Technical University of Denmark. So the idea of the TU is a university that is only devoted to engineering education, technical education, and our teaching is grounded on experimental research. We are one of the main universities in North Europe and in the world in the rankings. Every year, this is based mainly on our publications. We have a high ranking of publications, and this is based mainly also in the amount of international collaboration and collaboration with industry. We have 12,000 students, around 12,000 students. It fluctuates a bit every year. And these students are not only Danish, we have students from everywhere in the world. It's a very international environment. We are around 3,000 researchers. So the ratio between students and researchers is quite low. So students have a lot of accessibility to high-level profile and laboratories and so on. The teaching environment is very open, very collaborative, also in the spirit of Ørsted. And the learning environment is very open. The hierarchy is very low, so there is a lot of accessibility to resources and to personnel. While we are in this project, we belong to a group that is called Networks and Service Platforms, and we work mainly with telecommunication networks, optical networks, electrical networks, but also wireless networks. And we have worked for 25 years in projects related to networking, design, implementation, and management of telecommunication networks. And in the last years, related to softwareization and the programmability of networks. Also simulation. We have a lot of experience in network simulation, and this is what we have been doing in our previous projects related to railways. We have been working with railways for 12 years already, and we have been collaborating with industry and also in academic projects in the last years under the umbrella of Shift to Rails, like previous projects. And all of this also, according to the spirit of Ørsted, impregnates our teaching. We have created, based on this experience, we have created courses on railway signaling technology, and we have student projects and collaboration between industry and students. So going back to the main topic of the talk, I should present the LTE subsystem in Emulradio that is here in the circles. So the idea is to have an end-to-end transmission path so that we can attach some real equipment, provide an LTE radio access, and create an end-to-end transmission path based on a LTE radio access network. Our implementation is based on Open Interface. Open Interface is a free open source software that is compliant with the 3GPP standards of LTE for the different elements in an LTE network, the user equipment, the InnodeB, the MME, etc. The nice feature of Open Interface is that it's Linux-based, so it can run in off-the-shelf computer, in commercial computer platforms, with those that have sufficient memory or performance, processing power, sorry. Open Air Interface was originally offered by EURNEXe.V in France, but today all the software and the software releases are managed by a specific software alliance created for it. You can find here in the slide the link to Open Interface. You can download, you can install it, you can play with it. So DTU, together also with Université Eiffel in France, we have previously used Open Interface in some previous projects, in FP7 and also in Shift to Rail. And we have experience, we were happy with how it was working from a functional perspective. today, OpenAI interface is migrating towards 5G, and it was also one of the objectives of the project to incorporate some 5G features. Pitifully, the releases by OpenAI interface were not mature when we started to set up our environment, so we dropped the idea. But all what is presented here can be also extended to 5G once the releases and the software in our platform can be updated with the 5G releases. So this is a diagram of the setup that we have in our laboratory. So the idea, as mentioned, we have to have an LTE-based transmitter that connects to an LTE eNodeB. The eNodeB is the element in the LTE network that is collocated with the antenna in the radio access and makes all the signal processing and packaging, converting the data from radio to IP-based packets. So in our implementation, our setup, the eNodeB is based on release 8 on LTE and working band 7. This is 2.6 gigahertz, and the bandwidth, the width of the channel is 10 megahertz. So if we see the eNodeB is connected to the EPC, this is done through a switch. I will explain now briefly why and why not directly. And the EPC, that is the entity in LTE that keeps or that allows to keep data about UCC services and also some entities that perform routing in the network. The EPC is connected also through a switch to another computer that behaves as a receiver, which we have an IP server. So we have an end-to-end path to emulate this transmission of data from transmitter to receiver through the LTE network. As mentioned, we have here two switches connecting these elements instead of connecting them directly, and this allows to inject some traffic here and also here through this switch to emulate colliding traffic or competing concurrent traffic at the same time to the one that we are transmitting. So this green path here represents our data setup or data link, connectivity link. But if you see, there is also some other links here connecting all the elements in a common switch to a single computer. This is a control network that allows to have this single computer controlling all the other ones, so that we have a single point of management to the whole setup in our laboratory. And we have this computer also connected to our network in the university. So this allowed us to control the whole setup from our offices without the need to go to the lab or even from home or from outside DTU, connecting to the VPN of the university. So we have direct access to the elements of the setup. So this is an image of the setup in the lab. And in fact, this is not the lab of DTU, this is the lab of IkerlanRaul. And this is the result of the integration test when we set up everything. We dismantle the setup in our lab and we move it to IkerlanRaul and we put it together for integration with their equipment. So here we can see this first computer is this one, is the one emulating behaving as a transmitter, LTE transmitter, and the radio features are provided by a USB dongle, a Huawei USB dongle that contains a SIM card that is programmed with the data, the IMSI and so on, of a user that is registered in the entities in the EPC. We have here, this computer is the eNodeB. As mentioned, is the element collocated with the antenna in the radio access network, and the antenna and transmission reception capabilities is provided by a software-defined radio card. And if you see here, the output of the antenna of the card is connected to the antenna of the dongle via a radio cable. We did that, we could have used only the radio interface in the open, but we decided to connect with a cable to avoid any spurious interference that could affect the link that we were interested in. So we connected via cable, a radio cable, so that we avoid this external interference. So the rest of the elements are, as mentioned, the EPC, the receiver, and the traffic generator. And as you can see, all of them, they are conventional laptops. They are high rank laptops with a lot of memory and sufficient processing power. And the InnoDB is the one that requires more processing power, so it's based on a high level desktop computer. Also, we have the YAN server, the controller of the whole setup. We made a lot of tests. We made tests in-house in DTU. We made test integration also in Ikerlan, and also Gustav Eiffel made also some tests. Here in the setup, when we make the integration, we have two additional elements. We have the channel emulator in the radio access, as Raul has explained previously. This was the channel emulator by Ikerlan that was connected again with a radio cable to avoid any external interference. And also we have another element here. It was another computer that is this one here that holds an emulator of a backhaul network. And my colleague Ying is just going to explain after this presentation about this emulator and how we emulate it and we integrated it in the overall setup. And as mentioned, there is a presentation later by Marion where she's going to present all the tests and all the results. So my presentation stops here. If you have any question about the LTE setup, you are very welcome to do it right now, or maybe write it in the chat. It's up to you.
Okay, thank you very much, José. I think now in the we will continue with Ying, with the possibility of emulating the fixed network load before I present all the results we obtain. Yes, Ying, we see your screen. Ah, no more.
Yes, I will just because I have two screens and think this will work. And just 1 minute, it will work. And here in the Zoom, I will share the screen. And I need to choose. But can you see the screen without the?
Yes, with your presentation.
With my presentation. Okay, but can you see the screen with, let me see.
Yes.
With the comments or
no,
without
no,
comment?
The presentation.
The presentation, that's great. Yeah, so yeah, thank you, El. And my name is Ying, and also from the Technical University. So I will be to explain our work on the backhaul network and also the integrated software and hardware emulation platform. So I need to. So next, here is the overall figure. So the backhaul network emulation platform is highlighted by this red dot circle, and it receives the traffic from the LTE, Wi-Fi, or the satellite emulation subsystems. Its main function is to simulate the backhaul network topology and also to enable further analysis of interfering with the background traffic. So in the platform, a network simulation tool, which is called a Riverbed modeler, and previously is a well-known name, is OpNet, is used together with the system, is a system in the loop, is also in short CITO model. So I will introduce more in details. First, about the simulator that we selected is a discrete event simulator, and is well known to be used for network simulation. But please note that it's a commercial software, so the license is required. And also, this simulator supports one important model that we used in this project. It's called CITO, in short for System in the Loop. With a CITO package or CITO model, the simulated environment now can be connected and interacted with the external physical hardware in real time. and the packets that can be exchanged and converted between the simulated packet and the real packet. So as you can see from this figure, that the real traffic from the LTE open-air emulation setup is injected from a CTO gateway on the left side, and then after transmitted through the backhaul network, the simulated traffic will be converted again and just sent out to the application server. So in this way, so the real traffic, the network traffic can be connected, can be traversing smoothly through the whole system, from the physical to the simulated. And now our focus then with this setup, our focus then is to evaluate the impact on different network topologies, and also how we can injecting different background traffic in order to analyze the network performance. As Jose just explained, that the overall setup, so the OpNet or the backhaul platform is subsystem is also highlighted with this green dot frame, and it includes the OpNet simulation software with 2 CTO gateways. And these are 2 CTO gateways. In order to use them, so it's need to be pre-configured. For example, the real-time execution ratio need to be properly set up, and also it's so that it's ensured to be consistent with the real time. And so the two figures on the bottom they show 2 different network topologies that we have simulated just as an example. So we can program the network architecture, and also we can manipulate with the traffic types, and also to identify, to use this to make a case study. For example, if there's a link failure or there's a node failure, that's all can be done in the OpNet simulation. And in order to do that, we have done different tests. We have the integration test in IkerlanRaul at the beginning of this year, and the purpose is for the functional test, and and also how it's integrated with the open-air interface, and also the channel emulator. So the backhaul network simulator is shown in this blue, now is in the blue frame, and we have succeeded with the real life test for the connectivity and also the data transmission. Afterwards, there are a few tests continued and performed at DTU until July, and we started to look into the pure simulated traffic in order to verify how the different backhaul topologies can be implemented, and how the congestion tests can be performed with different traffic types and different traffic load. And then we do this with the CTO connecting, which means to have the hardware and software connected. And also what we have also tried, we have used the different devices provided in the OpNet software for the switch or router and so on. And all the tests are also use the app for traffic generation. Here's an example for some examples for how we do the test configurations and how the results can be obtained in the OpNet. So for the configuration on the figures on the top is we have the predefined attributes such as bandwidth and duration, and also the traffic flow that you configured here can be applied to all the links. And besides, we can also set up different traffic types in the application, the profile definition. We can then in here, we can choose the proper services as needed in the project. For the result, OpNet has its own statistical result collection, so that it can show the performance metrics such as the entry delay, jitter, and throughput. And for example, in the first figure, that's the background traffic is injected and the link bandwidth is overloaded. So you can see the delay is increasing, reach to a peak. It can also compare the delay into different scenarios, the normal or the overloaded. And also it can compare can give you the comparison for using different applications. Here we have, for example, if you're using TCP or using UDP, you can do a comparison in the OpNet. So as a summary, that in the project, we have integrated this simulated program with the physical setup and using this CETO interface in real life. And also we injected different simulated background traffic with the mixed application and the mixed traffic load. And also these analytical network performance are collected in respect of delay and the throughput. So our feeling that to use the OpNet as for the backhaul network simulation, so we can adjust the traffic parameter freely, and we can also dynamically change the type of devices, and it's easy to redesign the network topology. And also, as last but not the least, is the size of network can be extended and reduced easily in the simulation environment. So thank you. That's all.
Thank you very much, Ying. I don't know if there is any question, or I can continue with Raoul for the presentation of the result obtained with the OpenAir interface platform. So Raoul, I don't know how you want to proceed. I share the presentation.
Okay.
Okay. Okay. Oh, yes, I think I have to open it first. Okay, and then
I can share it if you prefer, Marion.
Yes, I have too much, as I have some of your presentation open as on background. I think it is why I cannot see the presentation. Normally now it's okay. Oh yes, you can share it,
Okay.
because I will do my best to.
Okay, so in this presentation, what we will see are the tests that has been done with the OpenAir platforms and the channel emulators. They are tests similar to the ones that have been presented for Wi-Fi, done with iPerf and so on, but in this case with two different platforms for OpenAir interface. One integration of the OpenAir platform from DTU here with the channel emulator of IkerlanRaul in the IkerlanRaul facilities, and an integration of both the DTU OpenAir interface and the one from the Univ Eiffel all together with the PropSim channel emulator. So, well, here you can see again a summary of the tests that have been carried out in the LTE part in this case. And again, we have done some reference measurements to see what happens with the OpenAir platform in the absence of perturbation of channel and so on, and then several tests for different channels. So this is a photograph that Jose has presented just before, in which we can see the integration between the OpenAir platform from DTU, that would be this part, and the channel emulator from IkerlanRaul. Similar to what was done with Wi-Fi, in the external part of the platform, we can find the iPerf client with the LT dongle in this case, and in the other part, the iPerf server that is connected to the backhaul emulator. So we do end-to-end test with iPerf. This could be the block diagram, what I have just said, the LTE dongle with the control PC, in the middle the channel emulator for both for uplink and downlink, and then the OpenAir platform, which is made of several devices, as Jose has explained, and finally the host PC, which runs the iPerf server. So for this test here in IkerlanRaul, we have selected these four channels. And what we use is a LTE dongle from Huawei, and as a LTE network, as we have said, the OpenAir interface. And again, we have used iPerf for the test. It has been 60-second tests with an average of 1 second, and for both TCP and UDP. And we have measured the throughput per and delay and jitter. So first of all, we have done a reference measurement in which we just put an attenuation, a 30 dB attenuation into the system. And well, as we have made some tests at different speeds at UDP and also tests of TCP. And what we can see at a first sight is that the results were very poor. I mean, the packet error rate, in the absence of any perturbance in the absence of any channel, it's very high. I mean, the best case would be 4%, and it's so strange that as the throughput lowers, the results are worse. So this doesn't make any sense. And as we will see later, it's related to the version of open interface that was used for this test was not ready for this type of massive tests with iPerf. I mean, they don't integrate very well each other. As Marion will also explain later, we have made some last time tests with the latest releases of open interface, and now the connection is far more stable. The obtained uplink and downlink results are very good. So it's a pity, but I mean, when we did this test, it was too early for open interface, and that's why we have these poor results. Similarly, once we have started with the channels, either with no fading or with very little fading, what we see is that the packet error rate, for example, get worse from 16% to 32 to 46. And similar thing for the TCP throughput, with it's very, very, very low. Even in some setups, the test crashes. Also, it's again because of the open interface release. This is a small sum up of what I have said. The obtained results were very poor, and these results cannot be a consequence of RF impairments, as some of the tests didn't have RF impairments. But I mean, if we don't take this into account, what we do see is that okay, as the channel get worse, the results get worse, even if they are much worse than expected. So this is the logical behavior. And the conclusions we raised at this integration is that the open interface is not prepared for this type of high performance testing, or at least the release of open interface that we used. For example, the automatic gate controller of the SDN hardware was not working properly on this release. We believe that in the latest one, it works much better. And well, Open Interface, it's a very interesting tool, but in this release was not prepared for handling these intensive network tests. So, Marion?
Yes, so I will say to you next. So I will present the test with integration of the two open-air interface platform, and with we have changed some parts. Next one, next. Here you can see the two platforms. So on the back of the screen, the DTU platform, and on the first position on the screen, the Univ Eiffel platform, and the Keysight channel emulator. Next one. So we have, regarding the test, the result of the test of Ikerlan and DTU perform earlier than the one we were able to perform due to the interruption of the lockdown in France. We have changed the eNodeB, so we have considered 2901 USRP and then 2944, which is more performant. And we have also changed the dongle in order to allow the downlink transmission that was not possible. And we observe sometimes some improvement, but more or less the same results. So next one. Just here that to show the first configuration Raul speak about with the signal observed on uplink and downlink with two spectrum analyzer. Next. Here some result with the wire connection in uplink and downlink. You can see that in downlink is much better. We obtain quite good result, and this confirms the explanation of Raul that the dongle is a commercial product able to cope with real-time signal processing. Compared to the USRP board, which are a bit not enough performant also on the automatic gain control. Next one. So here you have the comparison on the two last table. For example, we have the uplink comparison with USRP 2901 and USRP 2944 with 20 megabit per second. We observe quite similar results, in fact, and not so bad result, but you can see a small enhancement of the packet error rate, which is normal. Normally in with a wired connection. So next one. Here you can see the test with the wireless. So we have considered not so far position antennas, so they are 1 meter far away. So you can see the results. So the channel emulator is not active. And you can see here the result in downlink for different throughput. In fact, the software of open-air interface with the number of resource block allocated normally is much more adapted for 10 megabit and 20 megabit. And it could be an explanation of why we observe a bad result at low throughput. This is a bit strange regarding the jitter, for example, but for the packet error rate, it's correct. Next one. Yes, for the uplink, we observe curiously very high jitter for the low throughput. So we are still investigating, and we are discussing with the colleague of Open Air Interface on this. Next one. So as Ikerlan did with the colleague of DTU, we have tested before introducing the channel, we have introducing first a flat channel. So just with attenuation and the delay. So in downlink, we have good results. Also this observation of the jitter at a low data rate. Next for the uplink. And for the uplink equivalent result, and you can see that with flat channel, we have now good results in terms of packet error rates in uplink and downlink. Next one. So we have considered the same channel. So the ELI 3 taps. In this channel, we can consider that the maximum delay is not so high. It's 216 nanoseconds, and you can see, in fact, the influence clearly on the jitter that increase, and then in this table we have tested several speed with a classical Doppler spectrum. From the train is stop, and then we increase the speed up to 280, and after this the connection is cut, so we had problem of connection. So as Raul explained, we did the first test over 100 and 300 seconds to have this figure. And we have also performed tests with very long duration of 30 minutes. And Laurent will present after the model obtained. Next one. So you can see here the effect of the channel on the uplink direction. So always in uplink we have bad results due to the USRP. And we observe the bad result also in the software part with a lot of warning and error, it is the problem of real-time treatment of the signal on the Open Air interface version we are using. We implement the version available at the beginning of the project, and it was not realistic to change everything at the middle of the project, but we have Raul at Ikerlan have tested recently a new branch, the latest branch, published this trimester, and they obtained very much better results. So we can have now the result with the cutting 5 taps. What the main difference is in terms of maximal delay. Juan has explained that this delay affects a lot the performance and also the relative power of this tap, this last tap compared to the first one. And you can see here the result with a degradation of the performance. And obviously here we were not able to increase the speed higher than 200 km/h. This is compared to the LTE normal performance. This also confirms that the branch we are using for the software need to be enhanced. So next one. So you have here the figure for uplink, so always worst. Next one. And here we come back to a more easy channel. The maximum delay is higher than for the first one. and we have coherent results in uplink and downlink. Here we were able to reach 250 km/h. And then after, when we try to increase the speed to change the emulation, sorry, we have disconnection of the user equipment. Next one, I think we can skip and go next one. Yes, here just some figure with the test presented by Ying. So we did the test with the platform, including the load. We have used the same test setup than the one presenting by Ying. So we have no background traffic, and then we put 1 GHz background traffic after a while, and we did the test in uplink, and you can see the increase of the end-to-end delay and the increase and also some but we don't see big influence on the other result. In this case, we are using antennas. When we have tried to do the same test with the channel emulated, with a very big background load, it was quite difficult to the connection was quite unstable. So we were able to start then to transmit the data at different traffic level, and then the connection was disconnected. So we had not the possibility to do intensive statistical tests. So to conclude this presentation of what we have called the experimental assessment, so the idea was to prove the feasibility of the zero on-site testing with the Emulradio4Rail platform, considering LTE emulation and the real user equipment. So we succeed in that, even if we have observed problems. We have found where we need to enhance the system. The results vary with the type of railway channel and the speed. And we have discovered that we need to enhance, and hopefully Ikerlan has the time to implement the very last version of OpenAir interface, and they confirm that now uplink and downlink are working correctly. And what could be nice, but we have no time to do this, even if some colleague from Bombardier give us some possibility to emulate ETCS traffic. So I think it's the next step, because ETCS traffic is a very low traffic, and it could be nice to have an idea of the global amount with the adaptive communication system, where all the traffic will be sent on the same bearer, to have this final aspect. Then Laurent will present you what we obtained with long test, and this was the second output of the project, to be able to have emulation at IP level, thanks to the experimental assessment I have presented. Just the slide before for the perspective. So I just remind here some of the previous conclusion, that we have proven the feasibility of the zero on-site testing, but we need to have perhaps much more representative channels, also to have confirmation that these representative channels are really representative. And we hope that it will be possible to have the integration with industry that we were not able to do due to COVID for the LTE part, because Radiolab will present the success on the satellite part. So thank you for your attention. I don't know if there is some question in the chat before going to the presentation of Laurent, which completes my presentation.
So for the moment, there are no questions in the chat.
Okay, so Laurent, you can go on.
Oh, I hope you see my screen.
Yes.
Yeah, okay, so fine. So I'm going to follow up the presentation. Yes, that's it. So when the emulators are running, we are able to have a lot of measurement, a lot of tests at least. And we are able to have a lot of KPIs at the IP level, so in real time, in different scenarios. So the idea behind is to choose and to find the good models, statistical models for this KPI. Of course, the task is a bit is huge because you have many channel models, many interference models, many scenarios, many. So it's quite difficult to address all these, and we have to go step by step. I will just present here the first steps we have proposed. So the first step will focus on the UDP level with jitter and throughput. Of course, we could have more higher dimensions, more related stuff. This could be, this is future work. Majority of what I'm going to present are for Wi-Fi, but I will also present some downlink LTE results. So I will follow this plan. I will first have a first look at the measurements, just to explain a little bit what I see in the measurements. Then I will study in more detail the Wi-Fi case. And I will show that the methodology we have for the Wi-Fi is also available for the LTE. And I will conclude this talk that I'm keeping in time. So for instance, this is a look, I think it was in ERSICA platform, in the UGE and Univ Lille platform. It was for Wi-Fi, and this was measurements. I don't remember which channel model, it's 5-type channel model. And in the middle of the transmission, there was an interferer that was starting to transmit. So it was nearly a jammer because he was transmitting a lot, I think. But you can see the difference on the bandwidth, so the available throughput that the guy can use. The jitter also, it increases significantly after. The packet loss also is much more degraded when you have the jammer. So what we first idea is to have a sort of study of the distribution of this. So there I work on the jitter. The jitter is an interesting one for me, you know. And it's an important parameter. So we can, the first thing we can do is to fit distribution on this. So I will present this more in detail later, but you can see that it fits. So this is the first half, this is the second half. The good news in there is that the same distribution fit in both cases, approximately, it's not too bad. And you only have to change some of the parameters. So that sounds nice. What things that I will insist a lot during this presentation is that you have to look at the tail of the distribution. So if you see the log normal and the stable distribution, it's what we call heavy tail distribution. So this means that you need to be careful about things that happens not so often, but happens, because there you can have some high jitter, but with low probability. And if you use some more traditional Gaussian or stuff like this distribution, then you will not be able to represent these events, which are the ones which will cause trouble. And if I come back to my measurements, the second thing which is quite obvious, so I will not spend a lot of time on this, but you have a link between the different parameters you have. You cannot model independently the bandwidth, the jitter, and the packet loss. You have to have some joint models. So for the start, we have mainly work on jitter and bandwidth. So again, I will illustrate the methodology on one measurement from Ikerlan this time. So from Raul, I think it was the first easy case, which is flat fading. Not sure it's the easiest from a statistical point of view. So without Doppler, for instance, a train which is stopped. that's the easiest one. And you have, as you see, the bandwidth, the jitter, and the packet loss. As Ran mentioned before, the packet loss is 0. So that's the point. So there's no need to model this one. And I will model the two others. So the way we proceed, the methodology we use is first we study the jitter. So we are going to look for the best distribution for the jitter. So I present here a few distributions that I have tested. Of course, I could test much more, but if I find some that do fit there, it's enough. And then we perform a Kolmogorov-Smirnov goodness of fit test. So just to check if the distribution we propose fits with the data. It's one of many other tests that could be applied. We can discuss that also. And if a value of 0 is obtained, this means that you cannot reject the proposed distribution. So I'm not sure you can accept it, but you're on the good way. And then what we propose to do is to have a linear relation, not between the bandwidth and the jitter, but between the bandwidth and log 10 of the jitter. And okay, this is because the link is not really linear. So, and this works quite well. And of course, when you do that, you have an error of this model. It's not a direct transition between the bandwidth and log 10 of the jitter. And we model this residue by a Gaussian random variable. So I will show you what it makes. So in the case of the data in this not moving train, 4 distributions pass the test. So you've got a distributions that have similar behavior in some sets of parameters, and they do fit. So I also give the p-value. So the highest p-value you have, the better your test, your distribution seems to be. And the one which wins is a stable distribution. So I don't want to detail a little bit alpha stable distribution. I don't know if some people are aware of those. I know at least one is, but the idea behind stable distribution is that you've got an heavy tail. It means you've got a slowly decreasing tail of your distribution in comparison to the Gaussian distribution that we all know, where you've got an exponential decaying tail. So it means it decays very quick. So if you use a Gaussian distribution, you cannot have large events. That's practically speaking, that's what it means. With stable, you can. And it is shown there that you really need to take that into account because the log normal is also a slowly decaying tail. Gamma and Nakagami can approach this. They are not specifically in that case. So this is important. If you want to have a look on this, that is what it gives. So the blue line is the data, and the magenta is, in that case, I took the gamma, which must be the second case, and the stable. So if you look at the PDF, you've got a little bit of difference, but is it significant or not? Not that much. If you look at the CDF, so that's why when you present statistical results, you usually plot the CDF because it's much better. You don't see nearly differences, especially with big lines like I plotted there. So now I come to the second part. So I've got the jitter. I know a statistical model for my jitter, and I want to have a statistical for the model for the bandwidth. So I say my bandwidth is equal to something multiplied by log 10 of my jitter plus some noise. So I make a linear approximation. So I've got a straight line, which is the A log 10 of J plus B. The minus is no interest there. And there is, of course, a deviation of this, which will be the N. So I can calculate quite easily. I can fit the A and B quite easily. And this is the residue. So the difference between my straight line and the true value of the bandwidth. And you see, I can fit it quite well with the Gaussian distribution. So that's the way we do. I will to summarize, distribution for the jitter, linear relationship between jitter and bandwidth, and then an additive Gaussian noise. I will not detail all this, but we can do it quite naturally now for all the setups. So this is all these are Wi-Fi setups. The two last were made in Irsika, and the 10 first were made in IkerlanRaul. We have a sort of regularity in the model, so the stable is always a good fit. Sometimes, in a few cases, I think the log normal distribution was better. I think in this case, I've got to study why. The parameters of the distribution have similarities, but we have to further study that. Okay. So I will make all the conclusion in the end, but it's important. I come back on this. It's really important to keep in mind that you have to have, for the jitter, some heavy tail distribution. If I look at the LTE downlink, I can apply exactly the same process. So this is the measurements we have. These were done by Marion, I think, with the PropSim simulator. And we can fit, so in that case, the only which goes through the test is the log normal distribution. The stable does not, it's a close one. So you can see that even if it looks like it fits, this on this figure down right, it does not pass the test because it's, and this is perhaps due to, I think this is due to some oscillations you see there in the distribution, which are a bit difficult to capture. But we can discuss that later. And the link between, so this is packet error rate, so packet loss and jitter is very, very linear. There is a very, very strong correlation, and you really need to account for this. But our model still does fit. There is perhaps this little deviation there that I don't know if we have to take it into account. But the process still goes. So to conclude, so the platform allows to have a lot of tests, a lot of flexibility in implementing the channel models, in implementing interference, and then we can have we can define the models at IP level, at IP level for KPIs. We have proposed one first approach for the jitter and the bandwidth in the case of Wi-Fi and the packet error rate in the case of LTE. But of course, this has to be further improved. And one of the main conclusions is that some classical distribution are perhaps not the best fitted, and we have to look for more subtle models. What we miss for now is the time evolution of the parameters. Okay, and I think I will conclude there, not to be too long.
Okay, thank you very much, Laurent. Do we have any question on the chat before just the last presentation related to the platform, which will be very quick just to show you that we were able to pilot everything?
For the moment, there are no questions in the group chat, so
okay.
Feel free to write something here.
Feel free, yes, and everybody is lost or everybody is angry. But we have some more presentation before lunch, and just Ali, if you are there, you can
yes.
Yes, share your presentation. That is
okay. So can you see my screen?
Yes, perfect.
Okay, can you hear me? It's good?
Yeah.
Okay. Hello everyone. My name is Ali Sabra. Thank you for being here. And now I present to you the control PC that we have used during our test within the framework of Emulradio4Rail project. Just to describe, so it's already explained before. So each LTE system consists of 3 PCs, the EPC, the eNodeB, and the UE. And we have also the Wi-Fi platform that consists of 2 PCs, also as Sofiane and Laurent explained. The number of equipment to be controlled simultaneously during the final integration with the PropSim channel emulator is 9. So, and monitoring each PC of the whole setup is mandatory, mainly due to the unexpected frequent errors that we have encountered during the tests that we have done. So also this was explained by Marion, all the results that we had. And also the monitoring process should occur, of all platforms should occur simultaneously, because each element of, all the elements of the platforms are working in parallel. So any error in one element will block the whole system or affect the overall result. So therefore, it's complicated to initialize and configure and monitor by approaching each PC independently. So we had to think of a way to monitor and configure everything in parallel at the same time. So as a solution, we have considered the development of a control PC that can control remotely, configure, and monitor all PCs of each platform simultaneously. And this also helped us to detect any error in the system without the need to approach each PC independently. And this control PC should also have the ability, the capability of controlling the different platforms with the graphical user interface. It should also establish secure remote connection to avoid any third-party infiltration to the network. So to describe to you the hardware that we had used for this development, we have, of course, we needed the control PC itself. And we, of course, also the PCs that need to be controlled remotely. And in addition to this, all these PCs should be on the same network, all the equipment, including the PropSim radio channel emulator. So this is the network topology that we have considered. We have all the PCs of the different platforms with the channel emulator and the Wi-Fi of the University of Lille and the control PC. All of them are connected to, are on the same network. And for this network setup, we have used a switch and also the RJ45 cables. And notice here that some PCs are running on Linux operating systems, while others, like for example the radio channel emulator equipment and the Wi-Fi of University of Lille, are running on Windows OS. So this should be taken into account when developing the control PC. So this was about the hardware requirement. Now coming to the software. So to control all PCs securely with graphical environment, we have chosen the TightVNC. So TightVNC is an enhanced version of the virtual network computing, a graphical desktop sharing. And it also uses the remote frame buffer RFB protocol for remote access to graphical user interface. So we couldn't, for example, use SSH, like for example, Sofiane was describing before for remote connection, because not all people are familiar or are comfortable with line commands. Therefore, we have used this software here, the TightVNC. It also allows for upload files to the server, which are the controlled PC described before, from the client, which is the controlled PC, or download from the server to the client, so vice versa. And it also allows to set a secure connection with support of two passwords, the read-only one and the full control one. So the whole setup looks like this. Here we have the TightVNC server Linux version installed on Linux PCs, and the tight VNC server Windows version installed on Windows running OS. And notice that for the control PC, only the VNC client is installed, the VNC viewer. And this is how the system looked like during the final integration. You can see here on the table the control PC, and this is its screen here, just next to it. And here you can see all the systems of all the different platforms, University of Lille and DTU, Université Gustave Eiffel, different systems are being controlled by the control PC with graphical user interface. You can see here in the top corners the UE interface. Just beneath, you can see the EPC. And in the lower corners, at left and right, the both ENODs of DTU and Université Gustave Eiffel. And in the middle, this is the radio channel emulator, the PropSim radio channel emulator interface. And beneath, this is the interface of the Université of Lille Wi-Fi system, which is here. And everything was controlled remotely by the single computer here in the front. So this was all. Thank you all for your attention. And if you have any questions. Hello, sorry, Mario, I can't hear you. You muted your microphone.
Yeah. Thank you, Ali. And there is no question. Apparently, everything is clear for everyone. So we are in time. This is perfect. And I can leave the floor to Mohamed for the last presentation of the morning. We will come back to simulation. Which was a part of the project of pure simulation using discrete event simulator to test some scenarios. So Mohamed, the floor is yours.
Thank you, Marion. Can you hear me?
Yes, and we can see your screen. You just have to, yes, switch in presentation mode.
So, hello everybody. I'm Mohamed Kassab, an associate researcher to the University Gustave Eiffel. So in this presentation, I will talk about the pure simulation approach performed during this project with Riverbed Modeler Network Simulator. So the goal of this work was to show the capabilities of pure simulation to be an alternative framework to evaluate the performances of network architecture for railway context. And we make use of Riverbed Modeler, which is a commercial network simulator that was also presented by Ying in the PLMN part of this project. And this simulator is able to provide an interesting environment to design complex network architecture, advanced wireless modeling, and also realistic application modeling. And particularly for this work, the modeler offer a really interesting module for the LTE technology. So we use this simulator to propose a variation of performances offered to IP data flows exchanged between trains and the ground. And we perform this evaluation considering the LTE physical layer configuration, some radio disturbances, and also consider multi-radio access network in a real-world context. So let's start with the first part related to physical layer configurations of the LTE technology. So here we consider a set of study parameters, including the path loss model, the multipath channel model, the MIMO transmission technique, and the number of antennas at the trains and the ENODs. And for this study, we consider an LTE radio access based on the specifications proposed by ETSI for future rail mobile communication system. So here an overview of the considered LTE radio parameter, particularly the frequency band. We consider the extended UIC band at 900 megahertz and a bandwidth of 1.4 megahertz. We consider also parameter for antennas at the train and E-node-B, maximum power transmission, antenna gains, etc. And for the evaluation scenario, we consider one LTE cell with an E-node-B connected to the involved packet core and then to the application server. And we modeled two trains that are moving between the edges of the cell with a velocity of 350 km per hour. And we consider two IP flow per train, one from the train to the ground and one from the ground to the train, with a throughput of 0.75 megabit per second. And we, as a first set of evaluation, we consider the path loss model as a main parameter, and we consider 10 path loss models proposed by the simulator. And as a secondary parameter, we consider the multipath channel model, and we consider two models, ITU vehicular A and ITU vehicular B. And as performance indicators, we consider packet drop at uplink and downlink at the physical layer. This means that we compute the packet drop without considering the retransmission mechanism of the LTE technology. And for this indicator, we compute the average, and also we consider this parameter as a function of the train position. And as a second indicator, we consider the packet loss rate at uplink and downlink, and here we take account of retransmission mechanism of LTE technology. So here an overview of the obtained results. So we plot the packet drop at the physical layer at downlink and at uplink, and the packet loss rate at downlink and at uplink. And we can see that the main result that the choice of pathless model affects the packet loss performances at the physical layer, and we have the worst performances with urban micro 3GPP and the HATA urban path loss model. And the second conclusion that performances are better for the downlink, better than for the uplink. And also we can, comparing the packet drop at the physical layer and the packet loss rate at the IP layer, you can see that the retransmission mechanism of the LTE technology are able to overcome the packet drop at uplink and at downlink. And final conclusion here that the multipath channel models do not affect the performances for all the path loss model. So here we plot the packet drop at physical layer considering the train position for downlink and for uplink, and results at downlink show that the packet loss occurs mainly at the center of the cell, excuse me, at the edge of the cell, so here in blue, and only for the urban micro 3GPP, the packet loss at the middle of the cell, here in red, is quite significant. And for the uplink, the main packet drop are significant at the edge of the cell and at the middle in the cell of the cell, here in blue and in red. So as a second set of evaluation, we consider as a main parameter the MIMO transmission technique. So consider 4 MIMO transmission technique, antenna diversity and special multiplexing with 3 configuration, 2 code word 2 layers, 2 code words 3 layers, and 2 code words 4 layers. And as a secondary parameter, we consider the number of antenna at train and E-node-B and 2 configuration, 1x2 for the train and 2x2 for the E-node-B, and 1x4 for the train and 4x4 for the eNodeB. And as performance indicators here, we consider the packet drop at physical layer, the packet loss rate, the end-to-end delay, and the jitter. And here an overview of the obtained results. So we drop the packet drop at the physical layer, the packet loss rate, the end-to-end delay, and the jitter. And here results show that antenna diversity offers better robustness than special multiplexing for both antenna configuration, and the packet drop, as you can see here, increase with the number of layers of the special multiplexing technique. So it is not shown here, but the results show that the packet drop occurs mainly at the cell edges. And what explains these results is that the special multiplexing is less robust when there are bad radio conditions. And as we have a fairly significant cell size, we consider 8 kilometers, we have a lot of losses at the edge of the cell. So the second part of this work is related to radio disturbances. So the goal is to evaluate the effect of radio disturbances on the performances offered by an LTE deployment. And we consider as radio disturbances radio jammers offered by the simulator. So two radio jammer, a single band jammer, which offer a continuous transmission on a single fixed frequency band, and a pulsed jammer that offer a transmission on a single fixed band masked by a periodic pulse train in time. So as an evaluation scenario, consider also one LTE cell. We put a static train in the middle of the cell and a radio jammer 20 meters from the train. And we consider the same IP flow as the previous scenario. And here an overview of the obtained results. And we can see that the physical packet drop resulting from the pulsed jammer induced significant disturbances 4 times more than the single band jammer here in blue. And for the packet loss rate, we show that the LTE transmission mechanisms are not able to attenuate the disturbance, as here we have 30% of packet loss perceived by the IP flows with the pulsed jammer, in comparison with the single band jammer when we have less than 5% loss at the IP flow. Regarding the end-to-end delay, we have 45 millisecond delay with the pulsed jammer and 20 milliseconds for the single band jammer. And for the jitter, we have really not significant value, less than 5 milliseconds. So as a next evaluation, we propose a different scenario, as we propose a mobile train from the edge of the cell to the center, and we put a fixed jammer at the center of the cell. And here results show that the average packet drop remains stable within the 2 jammer until the train is halfway between the jammer and the eNodeB. And from this position, the transmission power of the jammer is no longer sufficient to disturb the LTE, the DL transmissions from the eNodeB to the train, so we have a decrease of packet drop. And as a second test, we put the jammer near the eNodeB, and the train is still moving from the edge to the center of the cell. And here we can show that the average packet drop remains stable during the train trajectory for the 2 jammer until the train is 120 meters from the eNodeB. So here we show that the transmission power of the jammer is sufficient to disturb the downlink transmission from the eNodeB to the train. But before this position, the jammer disturbance remained fairly limited, and the eNodeB is able to transmit data to the train, and we have not significant disturbance. as a third test, we put the jammer inside the train, and the train is still moving from the edge to the center of the cell. And here we can show that the average packet drop remains stable during the train trajectory. And in this, and we have a really little decrease when the train approached the E-node P at the end. And here the jammer is in a fixed position regarding the train antennas, so the impact of the jammer disturbances remain constant during all the trajectory. So as a final part of this work, we are interested in multi-radio access network technology, network architecture in a real-world context. So here we considered a multi-radio access network architecture associated to a multipath management mechanism. And we consider a real-world railway context with a realistic network deployment. And the goal is to show the benefits of such network to guarantee optimal end-to-end performances at the application level. And we try to evaluate the effect of radio disturbances on the performances offered to IB flows. So as a real-world context, we consider the Copenhagen main station as an example of high-density area. The station is the biggest train station in Denmark with a high train concentration. It represents a typical area where a classical coverage may offer insufficient capacity to serve all the trains, and is an interesting use case where a multi-radio coverage can be considered. So the basis of these use cases were developed by DTU within the PhD of Alexander Sniady. And what was modeled here is mainly the train station area and the tracks network. So we consider here a network architecture offering an LTE radio coverage to all the radio network, the railway network, with E-node Bs deployed along the tracks. And also Wi-Fi radio to cover the station area. So we have here a Wi-Fi access point that cover all the station area, the main lines that cross the station, and also the secondary section inside the station. And in this network architecture, the trains communicate through Wi-Fi and LTE at the same time, and all the trains are including two radio transceivers configured with different IP address and connected to both technologies. And also trains implement the multipath transport control protocol MP TCP. So as an evaluation scenario, we consider an LTE coverage based on ETSI specification and a Wi-Fi coverage based on the 802.11n version of the technology and working on the 5 GHz band. And we consider a mobile train within the station area, so connected to Wi-Fi and LTE, and this train is exchanging a download traffic with the ground, so a TCP-based flow with a mean throughput of 200 kilobits per second. And we consider also a pulsed jammer that operate on the downlink frequency band of the LTE, and this jammer is placed in the middle of the station on the route of the middle of the mobile train. So here we show the effect of the radio disturbances on the LTE transmission as a function of the simulation time. And here we can notice that the physical at the physical level in red here. So we have a growth of the drop of the physical drop when the train is in the in transit and the coverage of the jammer, and also we have a growth of the HIRQ retransmission mechanism of the LTE. And then we try to show the effect of the radio disturbances on the MPTCP transport flow, also as a function of the simulation time. So here we can show that the disturbance on the LTE impact data exchange at the transport level. So here we can see the MPTCP flow running over the Wi-Fi technology and the MPTCP flow running over the LTE. So during the period that the train is in the coverage of the jammer, we have a decrease of the throughput over the MPTCP flow on the LTE and a growth of the throughput on the MPTCP flow over the Wi-Fi. And finally, we try to show the effects of radio disturbances on the application data, so at the application level, also as a function of the simulation time. And here we plot the traffic as sent by the application server in orange, and the traffic as received by the train in blue. And we can see that despite the significant disruption on data exchanged through the LTE link and also at the transport layer, the application traffic does not undergo major disruption. And we can see that here in this the same period when the train is in the coverage of the jammer, the traffic received by the train is slightly disturbed, but without loss of data, compared to the traffic originally sent by the server during the interval and where the train is in the coverage of the jammer. So these disturbances remain minimal in comparison with the losses observed at the transport level and the link and the LTE link level. And this clearly shows that the MPTCP is able to improve the resilience of exchange to possible disturbances on radio technologies. So as a conclusion, in this part of the project, we proposed an evaluation of performances offered to IP data flows exchanged between trains and the ground, considering the physical layer configuration of LTE technology and also radio disturbances. And we propose a modeling of a real-world scenario considering an actual railway context and a multi-radio network architecture associated to a multipath management mechanism. And we tried in this work to show the capabilities of the network simulation framework considered to be an alternative to evaluate the performances offered by the network architect. And as a perspective of this work, we aim to take advantage of more features of the simulation framework to implement realistic application models of the railway context, such as control command, maintenance, voice and video applications, and also to model specific radio conditions like path loss model for tunnels, for example. And we aim at the end to be able to propose performance studies for real network deployment on actual railway context for to offer the ability to railway operator to evaluate the performance of their actual network deployments. So thank you for some reference that I cited in this presentation, and thank you for your attention. And if you have any questions, so please feel free.
So thank you very much, Mohamed. We have some questions in the chat. Nirina Rambello asks, for your test, have you also looked into the security measures to be taken when using Wi-Fi based solution? Have you used any encryption level to secure the data and on end-to-end basis?
Not really, because this was not the goal of this this evaluation, but it can be configured, and I think that system or like 802.11i will not really influence the performances at the data level, let's say.
Okay, and also Ingo Wendler asked if it is not he does not well understand why Jammer has been investigated. The message is not clear when SFN is used. What is SFN? You can unmute if you want, Mr. Ingo Wendler. No?
Single frequency network. Okay.
Yes. Okay.
So for the first question, we investigate Jammer. The goal of this work was really to show the ability of this simulation framework to offer a different type of evaluation, and we try to show that the simulator is able to implement Jammer and to show the impact of Jammer in a complex, possibly in complex network architecture, and the effect of Jammer on data transmission. But really, for the second question, I don't really understand the meaning. So the message is not clear when single frequency network is used. So I think that maybe you mean jamming we are not considering jamming coming from other network, or Jammer can be can come from malicious user. So I don't know if it's the meaning of the question.
Can you hear me in the meantime?
Yeah.
Sorry. Yeah. Okay. I cannot understand. We are using anyway a single frequency network. That means we are using always the same frequency. What is the value add to investigate the jammer in that sense? Because when we have two adjacent cells, they have more or less the same effect, to my understanding. Maybe I'm wrong.
Yes, but there is still effect. So if we have a jammer, this will cause some disturbance on data, and the goal was to evaluate this disturbance and the amount of this disturbance of a jammer.
And also the role of multiple TCP.
Yes. When we have two technologies, so we are able to show that the MPTCP and the multipath mechanism can overcome disturbance that come from a jammer on one of the two technologies. So you're welcome. I don't know if there is any more question. So I just, Marion, want to respond to the question that was asked this morning regarding handover.
Yeah.
So handover was not treated on this project, but we have previous work related to LTE and also Wi-Fi, where we consider train mobile over all the network, and we try to evaluate the effect of the handover on LTE and also on Wi-Fi, and we have several publications on that. There is also common work with DTU related to that.
Okay, so thank you very much to all the speakers of this morning. We are right in time, so thank you to all. Thank you for the question. I think it's 1 minute before the break lunch, so we have 1 hour. I expect you to come back just before 2 to have the presentation of the satellite emulation part and the integration with Hitachi by the colleagues of Radio Labs. So have a good lunch, and we will maintain the link and stop the recording of the session. Bye bye, see you in 1 hour.
Bye bye.